In this problem, we consider a hydrostatic dam made of concrete. The upstream depth of water is H1, the downstream is H2. Our task is to determine the reaction forces. I will determine them in terms of the forces per unit out of plane length. I prescribe the shape of the dam by the bases A and B, the height h, and the angle alpha. These four parameters are tied by an equation which we will establish later. We begin solving this problem by drawing a Freebody diagram, which involves the weights of the rectangular part of the beam, triangular part of the beam, the distributed load acting normal to the dam surfaces F1 and F2, and each of them is associated with hydrostatic pressure. Finally, there are three reaction forces Fx, Fy, and the couple. I place the reaction forces in the midpoint of the foundation. Next, I need to quantify every force marked in red. These are known forces. I begin with the weight of the block. The resultant force of this weight is the specific weight of the concrete times the volume of the block. The volume is A times H times L, where L is out of plane length of the beam, and of course the weight W1 has to be placed at the centroid of the rectangle. Next, I will proceed with the triangle. Again, the weight is the specific weight times volume, the specific weight gamma sub c for the concrete, the volume of the triangular prism, the base is b minus a, the height h, and the out of plane dimension is L. The upstream pressure has a triangular distribution, and the resultant force F1 is applied 1/3 from the base, and the resultant is computed as the area of this triangle. So this is the maximum value of the distribution F1 times H1 divided by 2. F1 could be calculated as the pressure times length. So F1 is the force per unit length in this direction, and the pressure per unit length in this direction generates this force by multiplying pressure times the corresponding area, which is the unit length in this direction times the length in the direction perpendicular to the picture. At any rate, F1 max is equal to P1 max times L. P1 max is computed as gamma W, gamma of water, times H1, and we obtain this expression. The calculation for the downstream forces is similar, although it's a little bit more complicated. Again, we're looking at the area of the triangle. The triangle has the base F2 max and the height L2, and F2 max is related to the pressure P2 max by P times L, and now the pressure is still computed as gamma times H, and in this case it is H2. And finally, if I express L2 in terms of H2 and alpha, I obtain the following expression. The force is applied at the centroid of the triangle, so along this line it divides the lengths at the ratio of 2 to 1. Now I can put together the free body diagram with the forces F1, F2, W1, W2. The orientation of the force F2 is given by the angle 90 degrees minus alpha. To write down the moment equation, I need to identify various dimensions that will be used to calculate the arms. Now I can use these diagrams to write down equilibrium equations. Sum of the forces on X involves the forces F1, F2, and F sub X. Sum of the forces on Y involves the weights of the dam, W1 and W2, plus there is a projection coming from F2. Finally, the moment equilibrium equation is written about this point. This point does not help me with eliminating forces from the equation as we usually do, but I like this point because I'm comfortable calculating arms for various forces involved in this picture, and therefore I choose it, and as a result we have a longer equation maybe than necessary, but every term is easy to identify. The first term is due to this force, this weight, then we calculate the moment induced by the force Fy, and finally the force in the downstream produces two contributions, horizontal one and vertical. Now let us solve these equations for the unknown reaction forces. I'll start with the first equation. It is rewritten first and then simplified, and so the result is F sub X over L is equal to this expression. Note that L nicely factors out, so that I don't really need to know what is the total length of the dam. What I need to know is what is the force per unit length. Also, the result is independent of the dam parameters, which is typical. In this case, what drives the horizontal force is the pressure difference, because the dam induces vertical forces only. For the vertical force, first I write the original equation, and then I substitute the values for W1, W2, and F2 determined earlier, and this gives me an expression for the vertical force per unit length. I would like to pay your attention that this term is the weight of the concrete per unit length, and this is easy to verify by recognizing that modulo gamma sub c, we see the area of the trapezoid here. The second term is the weight of a small triangle overhanging the dam in the downstream. Of course, this term would be equal to 0 if alpha is equal to 90 degrees, simply because the overhanging triangle disappears when alpha is equal to 90 degrees. Finally, the moment equation. It's lengthy, takes quite a bit of algebra to simplify it, and I will simply write down the result. The result does not look too bad, but it's also unclear whether I made any mistakes or not. So it would be a good idea to check whether this expression makes sense. To this end, I will express A in terms of B, H, and quad alpha. Please look at the original diagram and convince yourself that this is correct expression. Next, I will substitute this expression into the expression for the reacting couple, and I obtain this equation. Now I would like to check what happens if alpha is equal to 90 degrees. So the dam becomes rectangular, and in this case quad alpha is equal to 0. In effect, what this means is that this term, and this term disappear, and as a result we obtain that the reaction moment is only due to the pressure difference, and it's very easy to look at the problem for a rectangular shape and show that this is indeed a correct expression.